All right, welcome everyone. Welcome to Strait Science. Strait Science is an evening seminar series put on by University of Alaska Fairbanks Northwest Campus in Nome, Alaska, as well as University of Alaska Fairbanks Alaska Sea Grant. Both Northwest Campus and Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which is the homeland and waters of the Inupiaq, St. Lawrence Island Yupik, and Central Yupik peoples. So tonight, it just so happened that we have been nothing but inundated with news of storms, some with terrible outcomes recently to the south of us, and we are all interested in the storms. And tonight we have three speakers. They're going to tag team along, and they are, you can see them there, and they are on board the UA or the UNOLS research vessel Sekuliak that's crewed and manned by University of Alaska Fairbanks. And they are getting underway after, I think they're waiting for one crewman, right? Somebody's coming in late tonight, and you guys are shoving off from Seward, and they're going to pass Nome and keep on going straight north. So we wish you the best on that. So our speakers tonight are Maddie Smith. I believe she's the lead of the project, and she is an assistant scientist with Woods Hole Oceanographic Institution. We have Jim Thomson, who is a researcher at the University of Washington, and we have Emily Eidem. I hope I said that right. Sorry, Emily, if I didn't. Is an associate professor at Oregon State University. And with that, we'll let them take it away. And we're really grateful you guys are doing this as you're prepping and getting ready to tie things down and shove off tonight. Please let us know more about the waves, ice, and sediment situation during our fall storms. Thank you so much for being here, or being there.
Yeah.
Here.
Yeah, thanks very much, Gabe. Yeah, well, the disappointing thing is we were actually intending to be there in Nome in person presenting this, but we had some last minute logistic changes with the ship, and so we're leaving out of Seward rather than Nome. So unfortunately, we couldn't be there in person to present, but we will be shortly making our way further north through the Bering to study the interactions of waves with ice and sediment for this project called Coastal Freeze that we're going to talk about tonight. So it's a collaboration between our three institutions. It's funded by the National Science Foundation. Yeah, so just briefly introducing the three of us. Our team is made up of a lot of Arctic scientists in addition to the three of us presenting today. So we're working part of this larger group. Yeah, and so Gay already, you gave some nice introductions, but yeah, so I am Maddie, and I've been working in the Arctic since about 2014. My first large cruise was on the Sekuliak about 10 years ago, which is what that photo is from. And yeah, I've spent now a decent amount of time in sea ice, and I'm really interested in ice and how it's interacting with the changing storms in this region of the world.
Jim? And I'm Jim, and I've also been working up in the region for a while, and very interested in how these storms feed back with the ocean, and the ocean changes and how it freezes and then goes through these seasonal cycles.
And I'm Emily Eidem. I'm a coastal marine geologist. I grew up outside Anchorage, and I do a lot of work in the Harrison Bay region, north of the Colville Delta. And I'm also starting up a little bit of work back home near Cook Inlet, looking at tidal flats. So doing a variety of coastal things.
Yeah, and so our work here on this project, but also more largely is motivated by a lot of the important aspects of the system along the Arctic coastline. And that's the reason that we're here as scientists. But the coastline of the Alaskan Arctic are really rich places with diverse, unique ecosystems that have supported communities for a very long time. And coastal ice in particular plays a really critical role. When it's gone, the permafrost is more vulnerable to erosion, like you can see in this photo on the left from the North Slope. But it also serves as an important hunting and resting ground for marine wildlife. These photos of polar bear and walrus in the middle, and is also a really important platform for the communities through subsistence hunting and many more activities. It's the annual cycle of both the ecosystems and the community. The hunting seasons are tied to the cycle of this coastal ice. And so that's a lot of what underlies the rhythm of the science that we do too. And of course, the coastal ice matters also a lot in the Bering Sea region, as you know. So a lot of the fall storms happen that have the really big impacts like the one we just experienced, but also this photo is from Murbach back in 2022. These are happening prior to when there's no coastal protection from the ice, which would otherwise potentially buffer the coastline, and these storms are getting larger. And so just looking at from some of the data that helps describe these changes locally in the Bering Sea. This image is showing the winter ice extent over the last about 20 years in the Bering Sea region. And so that dashed line is showing this downward decline of the winter ice extent over the last 20 years. And if we look at that more in a map context on the right, the shaded red is showing the change in sea ice duration in days per year. And so in the area around Nome, there's a trend towards less ice by about 2 days per year, which is, yeah, a pretty substantial change. And that's coinciding at the same time with the changes in the waves and winds locally. So the winter wave heights are increasing. So in that figure on the left, the points are showing individual years over the last 21 years of wave heights averaged over the winter in the area. And so that dashed line is showing that it's increasing, that kind of trend, which is again related to these increases in wind speeds on the right, where you can see that there's a trend towards much stronger winds, which are, relating to these bigger storms driving larger waves, especially when there's not ice. So the formation of coastal ice during the fall freeze up then is a really dramatic transition that changes how these storms are impacting the coastline. And so transitioning back to the area that our project is focusing more on the Beaufort Slope. This video shows an example of what that transition at the coastline would look like, which may be similar in some ways to what it looks like in other parts of the Arctic, where we see that really dramatic transition. The ice starts to form and expands out, but it's not linear. It kind of will begin to form and then get pushed back and then eventually becomes continuous. And this transition from open to ice covered in the nearshore can occur in as few as 10 days or as many as 30 days in this region. And so just to emphasize that this can vary a lot what this freeze up looks like, both in when it happens, whether it's happening early as in early October to almost towards December. So it can be really different both in shape and timing. And so this is in general a season of really rapid change, but also a lot of uncertainty in what those changes will look like year to year.
And this is a video of what it looks like during freeze up. This is from a prior experiment on the Skuliak. And this is during an autumn storm, and ice is forming, and pancake ice is formed in this example. And the pancake ice is formed because the waves are there. The waves cause the ice to bump into its neighbor, and it starts to make these very round shapes, constantly shaving off the edges of its neighbor as it moves with the waves. And so this is a really common thing we see in an autumn storm. The air is cold, the ocean's been cooling down, ice is forming, but you have all this motion and you make these pancake pieces of ice. And this is part of a very coupled process where the waves and the ice are interacting. And this can be a way to make more ice because the pancake flows can grow ice pretty quickly. But it also, the ice will damp the waves. It'll make the waves smaller, so it can reduce the impacts of the storm. So part of the work we're continuing to do is to try to understand those feedback mechanisms, because it's really a two-way process. The other thing that's happening is the ocean is really responding just underneath these waves. And so here's an example, a schematic form of what that looks like. In the late part of the autumn season, there can be a lot of heat that is trapped just below the surface in this part of the Arctic Ocean, and that can be mixed to the surface. And so you can make ice at the surface and then release some of that heat from the ocean that was lurking beneath, and it can melt the ice, and you have this back and forth ice advance, ice retreat, ice advance that happens in the fall. So just like Maddie was saying, it's not one linear just marching forward progression each fall, but it's actually much more event driven, and the character of each storm changes that process and changes how the ocean is responding, and the waves and all of the weather are combining to produce what eventually becomes the winter ice pack. So you can see here is an example of the kind of buoy we're putting out. Many of these buoys, we've actually put out some of them already up in the North Slope earlier this season, trying to catch the whole seasonal projection or seasonal progression that's happening in that region. And that's what we're headed up to do, is to catch the rest of it. Emily?
Cool. So yeah, we're interested in this interaction between waves and storms and formation of sea ice in the fall, and the way that's sort of a cyclical process that evolves throughout the fall. But ultimately, we're also interested in understanding how that affects the shape of the coastal zone and coastal erosion. And, everyone in this region is very familiar with the fact that this permafrost-rich soil is very vulnerable to wave attack and erosion. And we have these conceptual models where when the waves attack permafrost bluffs, the shoreline retreats and you get erosion. And intuitively, you might wonder where all that material goes, all that sediment. And, one easy hypothesis might be to think that material eroded out of the coast just ends up depositing near the shore and maybe forms new shoals. But what we actually see is pretty substantial erosion of the seafloor below the waterline. So it's really easy for us to see coastal erosion above the waterline, but there's also erosion happening below the waterline. And we've been working recently in the Cape Halkett region, where we're headed to on this trip. And we compared new bathymetry data that we collected with the best available navigational bathymetry, which is from the 1950s, because we don't survey that region very often. And in that 70-year time period, there has been up to 3 meters of seabed erosion, or 1 kilometer of horizontal, basically translation of the continental shelf in response to that coastal erosion. So the seabed is eroding along with the shoreline. And that's really interesting, because even though we do have big fall storm events and there are some waves, when you look over the span of the whole year, this coastline still doesn't experience that much overall wave energy relative to a temperate zone, because it's shrouded in sea ice so much of the year. So as geologists, we've kind of been wondering how that material gets removed and how that seafloor erosion happens. And one of the questions we really want to pursue on this trip is this idea that the formation of sea ice actually helps facilitate seabed erosion instead of protecting the seabed from waves. And we think that what's happening is those waves come through, they have a lot of erosive power and they stir up a lot of sediment on the seafloor. And the biggest waves come during the fall storms when, as Jim mentioned, that heat is being stripped out of the ocean and the sea ice is forming. And so you have a lot of sediment resuspension, really muddy water like you see in these satellite images, and new sea ice forming. And that sea ice actually entrains a lot of that seafloor mud that has been mixed up into the water column. And you can see in these photos areas where you're starting to form that muddy ice. And this process tends to only happen in the fall. And the ice will continue to grow and accrete on the bottom after that. You'll get ongoing freezing at the base of the ice. And that leads to these thick layers of sediment trapped in the ice. And you can see those in pressure ridges. Sometimes you get uplifted blocks of dirty ice. You can see them if you take ice cores or cut ice blocks out. And in the spring, when the snow ablates and melts away, you can see large patches of dirty ice in the coastal zone from satellite images. This is an example from the Cape Halkett region. And as that ice breaks out in the spring, it rafts away and it takes that sediment with it and carries it away from the coastal zone. There's a little bit of muddy ice in this example from Point Ley after it has broken out, and it'll be transported elsewhere. We think that some of it ends up on the Siberian side of the shelf and a lot of it ends up in the deep Arctic basin, but it's getting removed from those coastal areas. So these storm impacts, the waves that form, the sea ice that forms in the fall, these are all also related to the shape of the coastlines and how they evolve over time.
Yeah, so Emily hinted at that how long it takes for this ice to get out of the system determines kind of where it ends up. But so to understand that, we need to understand how long the ice is also sticking around before it leaves. And so often in these coastal zones, the slushy ice that we're seeing initially forming in the fall will become the stable landfast ice that we see through the winter and spring. So the ice eventually is going to thicken over the winter and form these larger ridges, which can become grounded and results in more stable ice that moves less. So this video shows that transition from less stable new ice early in the season. So starting now, it's kind of these yellows of less stable ice right near the coast that expand out, cover a larger area, and eventually become more stable, which is the darker blue colors. And so that's kind of this this transition of this new ice into this stable ice. And there is a relationship between when the first stable ice forms and how far that stable ice ultimately gets, we think. And so this transition is really important because of the role that stable ice in particular plays in stabilizing the coast, also enabling winter travel and hunting, but also for being able to ultimately transport away things that are entrained in the ice. But even when that ice becomes stable, it isn't always stable, and it isn't always safe. Strong winds that happen throughout the winter can fracture the coastal ice, and we can see an example of that in this satellite image. This is Point Barrow here, and we can see these leads radiating out these kind of big curves over that large area. And there's different regimes on the shelf that can destabilize the ice in different ways. Along the North Alaskan coast, so it's outlined, the outlined study region on this slide, the landfast ice can extend tens of kilometers offshore from the coast over the inner shelf. And we can use satellite observations over the last 2 decades. This is work from Mackenzie Jewell, who's part of our project. And she's used that to detect large midwinter openings along the coast and the relationship to regional winds. And these show that there are large opening events that are associated with offshore winds blowing away from the coast. And when these offshore winds come from the prevailing east direction, the opening can be constrained to the outer shelf, so that pack ice is pulling away from the landfast ice. But when the offshore winds blow primarily from the west, which is less common, the landfast ice can actually destabilize, leading to energetic currents and waves. And the number of these large opening events over the last 2 decades of satellite observations, so in this lower left plot, those are the blue ones here, we can see an increase over that period. And so this may also be linked partially to a recent increase in the offshore or southerly winds. So some of this work is also indicating that deep ocean heat may be sometimes impacting the winter ice cover as well, and reducing the regrowth after opening, after these seasonal openings in the winter. So below the relatively cold surface water in the winter, which is primed for refreezing with these openings, are often deeper water masses that are warmer and saltier, originating both from the Pacific or from the Atlantic. And these waters contain significant amounts of heat, which can reduce the ice growth or potentially even melt it if brought to the surface through the process of upwelling. And this can often be enhanced around submarine features like canyons. So there, you can see in this image of the bathymetry, we can see Barrow Canyon and Mackenzie Canyon. And this example from near Mackenzie Canyon shows observations that have shown that these easterly winds are mobilizing the opening the pack ice along the coast. And so this can bring some of these warmer water masses to the surface and suppress the ice growth.
And I'm just going to interrupt for 1 second. This is Gay. If you can go back to that slide, where Mackenzie Canyon is for your audience, that little island right there in the dip in the blue inside the black box, that's Herschel Island. And Koktovik would be over kind of where the F is in Shelf, just to sort of give us a little bit of so that Herschel Island's in Canadian waters, and where I think it's Maddie speaking, the arrow would be Koktovik, the easternmost community in Alaska up in the Beaufort Sea. If that helps, just orient us. Thank you so much.
That's a great point. Thank you for pointing that out. Appreciate it.
Okay, so now we've come through the seasonal cycle and the landfast ice is formed and it's stuck at the coast. Now we get to springtime and it's less of a focus of the project we're doing now, but we have recent results from a prior project looking at what happens in the springtime. And so we just want to round things out and show you that for a moment. This is an example from Icy Cape, which is along the Chukchi side of the North Slope, so it's between Wainwright and Point Ley. And on the left-hand side is a satellite image where you can see the land, you can see the coastline, and you see the landfast ice, which in late May is very prominent. And then there's open water just offshore of that. And there are two positions shown on the map. One's kind of orange color and the other's a blue color. And those are two moorings that we had out for an entire annual cycle. And we could compare and contrast what we see for wave conditions between those two. And it's very clear that, of course, as soon as the ice goes away, the waves pick up. So out in open water, further offshore, there's wave activity starting as early as early May. But there are no waves observed at the coast for several months, really until the beginning of July. And it's only then that the landfast ice finally breaks out and leaves. And then we start to observe waves at that site. So this is a really clean example of how the landfast ice buffers the coast. It protects the coast, particularly after it's been through this whole annual cycle. So how much landfast ice is going to be available in the spring to provide that coastal protection? We think that really gets set in the fall, in these fall storms as things are formed. And then it goes through these winter wind events and the ocean heat is arriving and there's lots of evolution to it. But it's all part of this longer story of how that landfast ice gets there by the time we get to spring. So the panel on the right shows the time series of the wave heights that are measured at those two locations. And then the lower panel does this cumulative sum of those things in a metric we call the wave height days. So you can think of it like degree heating days. You can think of it as a way to say, how wavy is it at this site? And basically, because the landfast ice is there, it's about half as wavy. There's half as many wave height days as there would be without any ice at all. So it's an important aspect of coastal protection throughout the region. So now we want to talk a little bit more about our specific study and just answer the question, why are we doing this now? Why is this project timely? And it's because the sea ice in general, it continues to decline, continues to be in retreat. So both the amount of ice in general is in retreat, and then the days with ice cover in any given year are also being reduced, right? There's more open water, so we think there's in general more wave activity, and these processes are getting more energetic as we go. And we certainly see that from some prior results. We see the wave activity throughout the region on a decadal timescale is definitely increasing. That's a very clear signal, more waves. So where we're about to head is out on this ship, the Skoliak, which I'm sure you've seen and known before. And here's a nice video from John, who's out with us. John Giat did these videos and does photos for us. And you'll see, if you follow us on various social media outlets, you'll see more as we do this trip. We're headed out on this ship. We're headed to this region that's shown in the bottom left, which is Harrison Bay along the North Slope. So we're just on the east side, or sorry, the west side of Prudhoe Bay and Wixit, and then we're over to the other side of Utqiagvik, and we'll be there for a few weeks, and we'll be watching the ice form, we hope, to plan. And we'll be looking at conditions like this one, where there's, again, this pancake ice forming and the ocean is freezing rapidly. And we're getting to see that process, and we're going to see if any sediment is on the move while this is all happening, see if any sediment's entrained in the ice. And we're aiming to be able to map out what's happening in a picture like this one. This is a schematic drawing showing what we think is happening in the fall. So you can see the land on the right-hand side, the pack ice offshore, and the deep water on the left-hand side. And in between this complicated coastal zone where sort of everything's happening at once, right? There's weather patterns coming through that are cooling down the ocean. The ocean is mixing. The ocean is picking up sediment from the seabed and also maybe from the coast itself, moving it all around, all while the ice is forming, all setting up this annual cycle that we're trying to study. So our questions are, do the waves and currents help or hinder ice formation? We think at this point it's actually yes, and it's both, but it depends on the exact conditions, and we'd like to understand it well enough that we could forecast it. and how much sediment is on the move and where as this is all happening. Here are a few examples of some of our tools. Some of the buoys we will deploy are shown in the left here. So this is just putting these buoys out over the side of the ship. And these buoys send their data in real time via telemetry. Those of you who are familiar with the Backyard Buoys program, we now have our data going through that program. So if you're using that interface, you could see it. I will note it's only the Backyard Buoys, the web application. The phone application doesn't have these buoys yet, but we're working on it. So you'd want to use the web application to see the data from these buoys in real time. The middle video is a tripod that's going out. So the tripod lands on the seafloor and it collects measurements. And even though it's only resting on the seafloor, it actually is able to measure the entire water column because it looks up through the water column with a sonar, and it can measure the currents, and it can measure the waves at the top, and it can measure the thickness of any ice forming because the ice reflects the sound. And then there's the ship in the bottom right, and the ship is, of course, able to break ice and take us through the ice, and we make a lot of measurements from the ship. We always have someone on the bridge who's making qualitative measurements of the ice just visually, and then the ship has all the meteorological instruments, which are really important for our study. We have to know what the atmosphere is doing to know how it's forcing the ocean to cool. So that's a key part. The ship is not just a platform for us, but it's also a scientific tool as we're out sampling. And there's a little bit of a detail on our site here. Again, Harrison Bay. So if you are familiar at all with the North Slope, the West Dock is shown right here. So there's Dead Horse, and there's Prudhoe Bay and West Dock. These are the Jones Islands, and then this is the rest of Harrison Bay here. Cape Halkett would be off to the left-hand side. So we've set up 3 lines that go from onshore to offshore, because again, that's where we think the biggest changes are from the deep water to the coast. And we'll be sampling along those lines, and then we'll have moored buoys and those tripods along these lines. And we'll do that throughout the time we're there, and then we'll leave some of the equipment behind, and we'll come back and get it next year, which is something we've done in previous projects and really gets us that full annual cycle that we've been talking about. So there will be some more work next year on a smaller vessel to recover the rest of the sensors that are there. And this is one example of a really fun new technology that we're adding in here. And one of the reasons we chose these lines, you're all probably familiar with the quintillion cable because that provides your internet most of the time. And then it doesn't provide your internet when it's been scoured by ice and the cable's broken. Well, that cable is also a science tool for us. This is something really that Maddie's been pioneering and the rest of us have been helping with. But you can actually see little vibrations on that cable that are caused by the ocean waves. So we've been able to use that cable to study this damping effect the ice has on the waves. So this example here is the distance along the cable from the fall 4 years ago, when we first started doing this. And you can see that at far distance along the cable, far distance from shore, there's strong wave activity. And then close to the shore, there's no wave activity. And that steep drop off in between, that's what we want to understand. We want to be able to do that. And the cable is a great tool to do that because it's running all the time and it has very high resolution compared to having a few buoys out. This has a lot of points on it. So it's an exciting new technology that we're adding. Okay.
Great. So we also just wanted to talk briefly about some of the outreach and engagement for this project. Clarissa Zeller is sailing with us. She's from UIC Science and she's the community observer. And you are welcome to email Maddie. Her email is up there if you want to get on Clarissa's distribution list. I think the welcome email went out today about the cruise, but we'll be providing updates about what we've been doing each day and what we're planning to do the next day as we go. And we try to share a little science nugget in there as well about some of the observations we're making. We're also working with On Point Outreach to share what we're learning with schools, and their email address is up there if you want to get some info about upcoming live streams, and then as well as info about some of the various social media feeds that we'll be featuring for this cruise. But you should also be able to find us on social media if you search for Coastal Freeze. We have been wanting to connect with some school kids in Alaska, as well as connect with students at our respective hometowns in Washington, Oregon, and Massachusetts. you know, we've been hearing a lot in the news this week about some of the flooding that's been happening, and we want to go into our communities in the lower 48 and kind of raise the awareness about some of the issues happening in the Arctic and help people understand these vulnerable coastal areas. We actually started this outreach a few years ago. We've been going to the Kavioluk School in Kaktovik and building moorings and drifters with the students there to think about how we measure waves and how we measure some of these coastal processes. And then in the last few weeks, we've been going to middle schools in the lower 48 and looking at wave tanks with them to think about how sea ice attenuates waves. And that's been a lot of fun. And we have developed some lesson plans aimed at middle and high schoolers, and we have made those available. So if you know any teachers in your area who are interested in adopting these materials, feel free to have them reach out to us. So just to wrap up, this is part of a longer term effort to understand and help forecast changing Arctic coastal conditions. So we're really trying to understand the system holistically. We want to understand changes, you know, how these changes in storms are impacting formation of waves, how that impacts formation of sea ice, and in turn, how that impacts the coastal morphology and the shape of the coastlines and rates of erosion. And we're looking forward to continuing to engage and collaborate with communities to improve access to data. All this data will be made publicly available as we go through the project, and it help provide data to improve community resiliency and community planning. Maddie?
Yes, that's all we have to share with you tonight. But really appreciate, yeah, those of you who are here for listening, and yeah, we're happy to answer any questions. We do have a project website which will be linking to some of those resources that we mentioned throughout, and yeah, we're happy to take any questions and talk more about anything that you'd like to discuss.
All right. Well, thank you so much, you three. And I know you're busy getting ready. You can see that in the background, getting ready for your cruise. And we learned a little bit more about what it is you're going to be doing. So before we do questions, this is the time for anyone in Strait Science to show a little love in the chat for Maddie, Jim, and Emily. And we appreciate you taking the time. Sounds like we may or may not see you on your way back down.
Yeah, we're hopeful, but as we've learned, everything can change. So
Everything can change. Yep.
the hope is that we'll be coming back through on November 11th. So
yeah. All right. Well, we'll keep an eye out and let us know if you're coming to Nome. Shoot me an email, unless your logistical people are here, which we don't know. That would be great. All right. So with that, any questions? I know I've got a couple. So in 2021, we had a Strait Science by, I got to call it up here. There was a team of people. I think it was including you, Jim Thomson. It was Jennifer McKinnon, you, Jim, and Harper Simon. And it was called Bering Strait Heat Bombs. So is this sort of an extent, that was the water that's underneath, kind of rides up through Bering Strait underneath at a different, I think it was a different density, temperature, salinity, whatever. And it sort of encapsulates these chunks of hot water and then rolls those right up under the ice, and then they can pop up and start melting ice. Is this is a continuation of that?
Yes, there's definitely some continuation of those themes there, and there is in the summertime and into the late fall, there's a very clear signal of warmer water that's headed north through Bering Strait, and it's particularly salty, so that it's denser than the water in the Beaufort. So it gets to Utqiagvik and Point Barrow and Barrow Canyon approximately, and the technical term is that it subducts. It dives underneath because it's more dense than the surface water in the Beaufort. And so it takes that heat and it hides it underneath. And then it can swirl around and circulate and pop up in sometimes surprising places. And when it does, it can be substantial enough to melt some ice, at least thin the ice, and that can be a pretty big signal in some places. And there are some real patterns to that current in terms of its spatial routing and also the timing, you know, sort of this late summer and early fall timeframe. But we also, in that trip, we saw some real surprises too, in where it ended up and just how strong it was. It's really it's a pretty big fire hose of water that's headed north, in certain times.
Yeah. But that was a little more, I mean, here we are really focusing on this more coastal ice. And so I think there's a lot of the same kind of questions, but also a little bit more of this question of like, what does it also take to get that really under the very shallow shelf? Like how much of that translates to these coastal regions where we have the ice forming that's going to become land ice fast and protect the coastline. So kind of understanding that extension of those questions too.
All right. So I have another question. When you guys were talking about dirty ice, I think you said dirty ice, and you meant sediments in the ice. Is that correct?
Yes.
So dirty ice in the Bering Strait region can mean sediments, but it also can mean algae.
Yeah.
We have such, just as a thing to think on, we have such intense algae growth. I don't know what it's like in the Beaufort Sea by springtime, but we have these, you know, you auger down or the ice is cracking and spinning around or you're crunching through it and it's dirty. It's brown or golden brown algae. And so that was interesting to me. And it brought up a question that I've never heard the answer to. So I have heard from the science community, Western science community, that ice formation starts at the surface. But I've actually seen it myself out here, and maybe it's a Bering Strait regional thing, but people say, well, you know, the ice will start on the sediments, which kind of made me think about your dirty ice. The sediments, it'll start freezing and you can see it, you know, on the bottom, on the seafloor, ice. And it hasn't broken up and bubbled up yet. Is that, how do you, are we both right on all occasions here?
Yeah. No, that's actually a really fascinating thing called anchor ice. And it can form on the seabed. So it's called anchor ice because people have observed it nucleating around anchors. It can nucleate around old tires on the seafloor. It can nucleate on rocks and sands. And, you know, I think that in some places, silts and clays would be too fine grained for it to nucleate around. But in the Arctic, they've been bulldozed by ice. So it exposes really old consolidated mud. And I think anchor ice can probably nucleate around that too. And it
nucleate,
just like grow around, right? It has an affinity for some hard object. And there's really cool observations of it all throughout the shallow coastal zone of the Beaufort Sea near Prudhoe Bay. There was a lot of USGS work there in the 80s where they observed it directly. And when the anchor ice gets big enough, the buoyancy forces take over and it actually can break free from the seafloor and it rips up that chunk of seafloor with it. And that is a really great way to form a lot of dirty ice, is by having huge anchor ice growth and then having it break free and join the pack ice. And that's one of the reasons you can get like non-homogeneous layers of sediment in the ice. You can have sediment like we're showing here that forms during the storm season, but then you can have sediment wrapped up with the anchor ice. And in areas where there is gravel, you can have sediment as large as gravel getting into the sea ice that way.
I mean, I've seen rocks like that big.
Yes.
Yeah, it's crazy.
Yeah, it's a really cool phenomenon. And I don't think people fully understand the mechanics of it, but they do think that it forms preferentially in places where you actually have groundwater outflow through the seafloor because there's fresh water there that helps facilitate the ice growth. Yeah, it's really strange.
Well, thank you for answering that and giving it a name to me, anchor ice. That's helpful. I've seen it and you think, well, and people say, oh, no, the ice starts on the top. And you think, no.
Yeah.
I mean, yeah, but it does. But there's also this other thing. So thank you for giving that a name. All right. Anyone else in the audience? We've got some ice savvy people in the audience and they are quiet. All right, you ready for another one?
Sure.
Of course.
So when we make ice in the Bering Strait region, we're so shallow that the salt that's captured, you know, when you first freeze ice in the fall here, you wouldn't make a cup of tea out of it. it'd be too salty. It'd be terrible tasting tea. But if you go in the springtime and you go pick up some ice and make a cup of tea with your camp stove on the ice, you can have a cup of tea and you don't have to, you didn't used to have to bring a water jug. So that brine coming out of the ice all winter, that's important for us down here. We're so shallow and it kind of sets up this very cold water barrier. And I'm wondering how does that work? Or maybe that's not an appropriate question for you guys. I don't know, but in that deeper, but you're still working near shore. I saw that picture where you have the open water, the one that Jim was talking about. And then you have that chunk of ice that's been rooted out and it's just kind of hanging there. And then you have the shore. Kind of like that one. It had a blue and a yellow dot, but that's okay. That'll work. And so my question was, when you've got that, does that brine rejection, oh, the one more back. You had it. One more back. Oh, no, that wasn't it.
I think it was this one.
There you go. That's it. Yep. So in there, look how nice protected the land is, right? And then you've got, somehow it opened up. So is there anything up there or in the deep, deep water on the north slope that when you're talking about this ice, this land fast ice, which has been given out that salt, I would assume, all winter, does that have any effect or a different kind of effect than it would for us down here because we are so shallow? Or is that not something you're looking at? I'm speaking ignorantly here, other than that's a fascinating process that is really important to our ecosystem. And I didn't know if it helped hold ice or if it kept the water extra cold, that sort of thing, near shore.
You mean a difference in the brine rejection because of the water depth?
Well, the water temperature, right, it makes it very, very cold, and that's important for us. It sort of creates a stable, cold, briny pot of water. But where you're working, I think it's a little bit deeper, isn't it? Or maybe not.
Well, that's pretty shallow, actually.
Yeah.
It is very shallow, and I know through the LTR program they've measured salinities of you can get a layer of like 0.5 meter of water that persists under the land fast ice where you have salinities of like 70 to 100.
Yeah.
And it's just trapped there, and that's why it doesn't freeze any further toward the bed.
Yeah.
Yeah.
That's
Does that have an effect on keeping the ice longer or not? Or, maybe it accelerates it. I don't know. To get out of there. It's too salty.
If something's very, very salty like that, it can limit the mixing because that extreme stratification, that's the word we use, keeps the layers kind of all in order, and it's very hard to take that heat that may be even deeper and bring it up to the base of the ice where it would cause it. So that can be it's sort of in the vertical dimension, a buffering mechanism, because if you've made this really very strongly layered ocean below, and that the layering doesn't want to mix, so that is an effect.
Yeah.
And certainly,
So you want to see that
Uh,
land fast ice is such an advantage for a coast. Not only can you keep the wave action down, but you could actually keep it from melting faster.
I mean, I do think in some way the fact that it like kind of traps the water underneath it to like minimize in the spring at least, like minimizes the mixing of other water masses into it, probably does provide some protection.
From a Bering Sea heat bomb.
Sure, I would think so.
Maybe.
Yeah.
That's interesting. Thank you.
It's an interesting question. Think more about it.
All right. And just for a fun fact for today, so I don't know how much, you guys have been busy all summer and you're all over the country, and we were reaching surface temperatures off of Nome in the summer here that was 63 degrees Fahrenheit. And we were measuring at just right here off West Beach, just going down to the waves and plopping your thermometer in. We were getting 60 degrees, 60.1, I think. I could look up the date. And the Chukchi was remained colder because it was a very interesting setup. We had a lot of hot water down here in the northern Bering Sea, hot. And we were sending it right on through the Bering Strait. I mean, hot. And the Chukchi Sea kept its ice quite long, more old times, I guess you might say. Not dramatically, but it kept it much longer than we've been seeing it recently. And so it was an interesting setup, having very cold water and then very hot water coming through the Bering Strait. It was a very contrast. And I just went to the beach today for those in Nome, and I went down to West Beach and we put a thermometer in the water and it was 5 degrees C, which is 41 degrees Fahrenheit. And that I was sort of surprised. Surprised, not surprised. I was at Diomede last week of September, and I was measuring between 38 and 40 degrees Fahrenheit. Just right off the school at Diomede, north of the helipad and then south of the helipad. And just wanted to let you guys know, it seems like it'll be interesting to find out what you see with your water temperatures. I think I put in the chat a little picture of the National Weather Service today's, and that's a pretty gross cartoon, those guys, but it looks like there's a little green patch trying to grow there or something.
Yeah.
We've actually been getting some nice, so the Alaska Weather Service has provides some really nice support for us working in the region as well. So they've been providing like similar kind of analysis of the area where our instruments are and where we're going to be working, and are starting to show some freeze up right along the coast there, and kind of incorporating both the sea surface temperature products, and we can see that they're getting actually pretty close to freezing. I mean, towards the outer edge of where our array is, it's still in, I don't know, maybe 2 degrees Celsius. So I don't know, it's above freezing still, but it's getting close. And we can also see that in the moorings that we did put out earlier, like in early September, a number of those have water temperature at the surface, where we can see as well that they're the ones especially closest to the coast are starting to see near freezing temperatures, which is, it's cool. So we can see that gradient and also that really strong change over time, like you're saying, Gay, that you're seeing there. Yeah, definitely happens pretty quickly.
Yeah. And yeah. And I think that was it for me, other than, do you think when you get it figured out, do you have any estimate of, I mean, we used to have land fast ice. Can you take what you're learning up there and maybe give us or is it so dynamically different up in the north that trying to determine when we may, I don't know, we're hurting down in the Bering Strait region because we don't get ice anymore on the regular schedule. And so we're later to form, it's going to be tough. I think if the water's 41 degrees, we got a lot of water to cool off here still before we see ice. And then we have open water. Last year was a really good year where we lost our landfast ice February 11th, right? We didn't lose it, but it cracked offshore and moved. So that was never heard of before for February breakoff, when we really didn't get it until December, November, late November, December. So we only really had that in place solid in front of Nome. I can't speak for the rest of the countryside, but it was not very good year for our landfast ice. And so we're seeing these dramatic landfast ice issues. Anyway, do you think when you get done, you might be able to extrapolate and sort of look at the Bering Strait region, or is that so different we're not going to benefit?
I mean, I think there's definitely like lessons of what we're learning, like in terms of understanding how the heat that's in the ocean relates to the ice formation at the surface that we can translate. I mean, this project does not explicitly have any like modeling or forecasting, even for the area that we're working. We're really trying to understand the processes but I do think some of it translate to the region and hopefully be used to improve forecasts and those types of things there as well. Do you have any other thoughts on that?
Well, very, very good, and good luck to you on getting that done. We need all the help we can get, I think, and the science we can throw at these issues, both for the North Slope.
Project in that area someday too. Yeah,
absolutely.
Yeah, we're all about the ice, or it's very dynamic now.
Yeah.
All right, nobody in the audience, raise a hand. Any questions? This is your chance to get these nice people before they shove off. And they got to get through Shelikoff Strait.
Yeah, wish us luck. It's gonna be rough out there.
Yeah, it is going to be a little bumpy, but you're on a good ship. Don't worry about that.
Yeah.
All right. It's a silent group. That's all right. Next week, we have on Tuesday for the next Straight Science, we have Tuesday night. We're going to have Rick Toman and Anjali Shah, and Anjali is here listening in, and they're going to talk, they're going to do their review. Rick and Anjali will be reviewing what we've gone through this summer, and then with an outlook for fall, and also extreme events. And so you can imagine we're going to talk a little bit, I'm sure, hear a little bit from Rick about what just happened here in the YK Delta as well as the Bering Strait region. And they're also having on Wednesday, we're going to do a little something different. And Wednesday, they are having, they want to have people come by Northwest Campus and talk to them about Murbach and about Halong and other extreme events that we have been recently endured in Nome and the region. And so come on down to Northwest Campus. I can't seem to open my flyer, but it looks like 3 to 6 p.m. on Wednesday, October 22nd. Come on down to the Northwest Campus. I would say the main building, and you will find Rick Toman and Anjali Shah, and they just want to talk to people about storms and hear more from actual people who've experienced Murbach and Halong, even if it's us. And with that, there you go. Thanks for the great talk. So complete, no questions. Wow, you guys nailed it. Nailed it. Well done. Thanks, Jim. At least we know that. Yep, there, and you can give a clap thing. That's awesome. There, Anjali, thank you. There. It's good. Yeah. Ed Plum, surprisingly quiet.
I was talking all day.
I know you were actually, so this is probably like dreamy just to watch other people have to give their talks.
Yeah, actually it is pretty nice. Thanks for the talk. Appreciate it. Have a good trip north.
Thank you.
Appreciate it. Thank you.
Yeah, and I think you guys will be amazed at how much traffic you're going to encounter. Ship traffic. There is a lot of ship traffic right now on, as you'll probably see it as you're coming through the Bering Strait region, but it's something. We are 2 weeks from Halloween, or November 1, and it is really different. The Port of Nome is still open, and we have all our activities still going on. So it's we may see some snow this weekend, but that's about it. Well, hopefully it'll be white when you pass by.
Yeah, looking forward to
So
it.
thank you guys, safe travels, and let us know if you're going to pull into Nome. We'll roll out the red carpet.
Thanks.
Thanks, Gay. Thank you, everyone.
Thanks for
All
organizing.
right. Have a good night, everyone.